Oi, what is good, y'all? We are back with part two of our Flash attention tutorial. This, of course, is lesson 10 of our Triton series, meaning if you've not seen the prior ones, you should probably go back and watch those. Things are not going to make sense if you don't do that, right? In the last one, we did our forward pass, got that thing all tested and benchmarked up and running, and now we get to do the backward pass, right? We are going to use actually the same code file we were working on last time and build off of it. Also, as always, the GitHub repo link in description has all of this stuff, not just this file I'm writing, but actually a more heavily commented version of it, to where if you wanted to, you could not even watch this video and just go read through that file. I've got paragraphs of comments there explaining exactly what's happening. So yeah, let's get to it. So we want to do the backward pass. We're in our test right now, right? But our test for our backward pass. And first up, just Triton. How do we make the backward pass actually happen? We have not yet written our kernel and our wrapper for our backward pass. We're gonna do test first. So our gradient DLD out is going to be equal to 0.1 times torch.random like. It'll be the same shape as our queries. And then Triton output, we already have that from up here in the test, and we can just do a dot backward on it. DLD out will be the input to our backward, along with retain graph equals true. All this does, I covered it in the last tutorial on layer norm. It allows us to keep the same backwards gradient and not remove them all when we want to go back and do it again for PyTorch. Usually you would not use retain graph equals true unless you are doing testing against PyTorch like this, right? So then we say, what are our DLDQ Triton, DLDK Triton, and then same thing for DLDV is going to just be, we want to disconnect the gradients we just got from this backward pass, disconnect it from the actual graph, so we can do the same thing with our PyTorch version. So to disconnect it, we're going to do underscore dot grad dot clone. That's the actual disconnect part for blank in, and then queries, keys, and values. And then just to equivalent of setting gradients to 0, right, is q.grad, k.grad, and v.grad equals none for all three. And then the backward fat pass for PyTorch, we're going to take our reference output and run dot backward on it with the input of DLD out. Again, retain graph equals true. I think I could actually not do retain graph equals true on this one, but got to make sure we try not to change my shittily written code live on video. I don't want to mess with anything. I believe, though, you could probably not use that retain graph equals true, DLDQ, because you only needed it for the actual the Triton run, right? DLDQ reference, our PyTorch, same thing, K, and V, same thing here, just separate them. I don't know that we actually need to, but we do need to do the actual clone parts, but we do need to at least grab them, right? For blank in Q, K, comma, V. I believe I was just being lazy, and that dot clone is unnecessary right there. And then we do Q dot grad, and we also probably shouldn't even need to set this equal to 0, but I'm not going to change my code now. And as you can tell, I was just lazily copying and pasting everything, and it still works, so no biggie. If you wanted to do more tests, like if you had multiple different kernel sets of each other, then you would have to do this for each one. Then we go to our actual testing. I'm going to compare them and say torch.testing.assert close DLDQ Triton, DLDQ reference, our absolute tolerance as defined earlier. We're going to do 5e negative 3, I suppose. Hopefully that actually works out. I don't remember if it actually does, honestly. We might have changed that later. I always either use 1e negative 3 or 1e negative 2, and 5e negative 3 is halfway in between those, so it shouldn't be an issue. 1e negative 2 is kind of pushing it in my mind of how high of tolerance to use. But when you care a bit less about perfect numbers and more about speed, it can sometimes be useful. In general, though, if you can write kernels that fit to 1e negative 3, that would be preferable. But I believe here we're only matching consistently 5e negative 3. passed backward. Boom, our test is done. Also, just to fix our benchmark, we can go ahead and remove that. Now, when we call benchmark next time, our code was already written in here from previously. And I'm not going to get super into our benchmark code. It's the same as always. But moving on to our wrapper, right? We already have that torch.autograd.function static method forward. And we now have to do separately from that a static method backward, right? And then as with all PyTorch backward methods, you first put in that context object useful for saving tensors and values and whatnot, and then the actual gradient of interest, DLDO, we'll call it here. I think we called it DLD outs down the test, but same thing. And then we want to grab all of those tensors that you see up above that we saved inside of our context object, as well as ctx.grid, as well as any other values that we saved in there, any floats or scalars or integers, whatever. Scale equals ctx.scale. And then all of our integers that are our dimensions, bh and dh equals ctx.dh, right? And then what we need next is we need to pre-allocate our gradient tensors, because right now if you were to do q.grad, by default PyTorch sets that equal to none. None writes, but we need to actually pre-allocate it and then replace that. So what do we say is we say dldq torch.empty like q, right? And then same thing for the other two, for keys and values. Not really necessary, but I'm going to go ahead and make them like their own matchup counterparts. And then a little assertion. This isn't even an assertion, actually. This is just us being lazy. In the previous, in the forward pass, we were not lazy and we actually used specific strides for everything. Here now we are going to be lazy and we are instead going to say, you know what? DLDO better be continuous because I don't contiguous because I don't want to do all that stuff with the strides like last time. I want to input fewer strides. And so we're going to go ahead and say if it's not already contiguous, which it should be based off our code, but whatever. If someone were to use a kernel in some other format, maybe it wouldn't be. We're going to go ahead and make it contiguous, which shouldn't be a crazy operation or anything. Hopefully, it would just be changing the actual strides sort of the tensor. But if there were a lot of like PyTorch or torch.reshapes or torch.views, then maybe it would be an actual full-on kernel call memory op. But we're not going to worry about that here. We're going to assert, once that's continuous, we can assert q.stride equals k.stride, v.stride, o.stride. And doing it this way versus our previous forward kernel, there's really no difference. It's just like you can choose either way, and it is an efficiency thing of, keep in mind, if you let tensors be not contiguous, aka what our forward pass did, then potentially these tensors could have all crazy different actual ways they're stored in memory, and it can be slower to read a tensor from DRAM if it is not contiguous and has a very weird setup, versus if it is contiguous, especially reading along that final dimension DH, should be as fast as possible. So this kernel here would be more general and slower, but not have to call any prior contiguous assertions, whereas here we are potentially calling a full-on little PyTorch kernel to make this contiguous, and then we are asserting these should be the same. We can pretty fairly assume this should all work, I believe, but it's just a different way of doing things that's a very minor choice, but might matter efficiency-wise if you're getting very, very picky and in the weeds. Delta equals torch.empty like. I'm doing it with this way with the strides just for sake of showing the other way of doing things. But really most of the time I would do the less lazy way and I would use individual strides. It's more clear as to what's happening. But anyways, our next thing, we are pre-allocating a tensor called delta, torch.empty like LSE. It just happens to be the same shape and everything as LSE. There's no actual connection there. So it is of a shape B, H, and N. And then what we're going to do is we're actually going to call an initial kernel that's going to pre-compute certain values, these values that we'll call deltas, and that this will pre-compute that in its own kernel, and then separately we'll call our actual primary kernel, right? So let's say our pre-computation grid is lambda meta triton.cdiv n meta pre-block size row. We're going to parallelize across that n dimension in the case of this kernel, as well as b times h split across batches and heads. Notice that our parallelization PID definition across n comes first. It is the primary axis of parallelization, the first one. And so uh, PIDs that are near each other on this axis will end up on the same SMs, whereas PIDs on this axis will all like that are different or even like the same will almost always end up on different SMs, right? That are if it's a different PID on this axis, chances are that's a different SM. And it may or may not be the same SM if it's the same PID on this B times H axis. Then we say attention backward preprocess, right? And we call our preprocess grid. And what are all inputs going to be? So this pre-processing stage, we're going to add in our outputs, the derivative of our outputs, and our delta that we're going to put values into, and then strides of our output. Remember earlier we asserted the strides are the exact same, meaning these can also be used as strides of queries, keys, values, and the derivative. Whereas what might not be the same is delta.stride, right? And then finally, these might be useful, the actual sizes. Once we have pre-computed all of that, we're then going to call our primary kernel. Let's do the actual pre-computation kernel first. I'm going to write it just right above the total wrapper. Let's copy and paste this in rather than writing it all out here. Just like the forward pass, I'm going to set it up so that you could do auto-tuning if you wanted to, but I'm just going to choose one value for everything, right? I'm going to be pretty lazy. Number, stages, and warps always by default are an option in Triton, but the only one that we actually define for ourselves is our actual block size here, and then our Triton.jit. We're going to define our kernel, right, with all of its inputs, O, DL, DO, and delta, but of course these are supposed to be pointers to the first entry of those tensors, not the actual tensors themselves. Then we say stride O along each dimension. What we can do here, we can copy and paste this thing a little bit quicker if we go ahead and we say stride of O along batch, stride of O along heads, and then along the sequence context length and the head dimension. You know what's crazy is I actually forgot entirely a whole line right here. I'm not even sure why we separated them. This is a kind of a redundant line. Basically, in the code that I'm looking off of off screen right now, this is what I did, is I actually had DL, D naught, DO of strides as well. These should all be the exact same as O.stride, so this is a redundant line, honestly, but I don't want to change my code now and get confused later, so we're going to keep it in. If you want, you can go ahead and not include this, and it should all work just fine, because they're the exact same values, but for sake of not having to deal with bugs later in my lazily written code, we're going to leave them both in there as separate. Then we can go ahead and say these strides of the delta one, right, of B and H, and the sequence length, and then N, D, H, which should be a compile time constant, and pre-block size row, same thing. All right, and now if we go ahead and grab that index batch head, so the actual second axis of parallelization, axis equals 1, right? So there should be B times H PIDs along this axis is the actual number of them, and then versus row is the other PID, right? This is the primary one we actually care about. Axis equals 0. And we are just going to move down that context length dimension of O and DLDO and use those to compute delta. So row offsets equals row times, what's that? pre-block size row plus TL.arange 0 pre-block size row. Then our column offsets is TL.arange DH, and mask equals row offsets less than n. We are only masking along sequence length, not also along the head dimension, because we did an assertion in the forward pass. Actually, I think it's right here, right? Yeah, that confirms that this is always a multiple of 32 and therefore is never going to actually need masking in a warp. So no big deal there. If you were to remove this assertion and support any given shape of the head dimension, you would have to add in masking on the head dimension. Now we're going to load rows of the output matrix of O. We're going to load pre-block size row like that. We're going to load this many of the rows, right? So O pointer, let's first move it, index BH times stride OH, right? So we are moving our pointer to the first entry of O all the way to the correct batch and head, for which you can use just the head stride, because then the batch gets included in it when you actually have multiple number of batches. And then we say O offsets equals row offsets none times stride ON plus call offsets none times stride ODH, right? And then we can actually load in our block of the output, TL.load O pointer plus O offsets, mask equals mask, and then make sure it has the correct number of dimensions. And then we say other, we're going to be just 0 values. I'm not sure if it actually matters here. Wait, yeah, it's going to matter here because we're going to do a sum later, I think, right? So we do want to make sure we specify masked out values equal to 0, not just none. We're going to see later we do a sum operation, and zeros, of course, don't affect a sum. And then we say DLDO pointer, do the same thing, is move it to the correct batch and head, stride OH. Then we say DLDO offsets equals row offsets none times stride DLDON plus call offsets none DLDO DH, and then we can load in DLDO, our actual derivative, TL.load. We're going to see why this precomputation is useful later. This precomputation here we're about to do in this little tiny kernel is equivalent to an operation we would have to do anyways in the primary kernel right later, and we'll see that equivalency later. TL.load DLDO pointer plus DLDO offsets, mask equals mask, none, and other equals 0. I suppose I could have just included this piece in my first definition of the mask, I guess, but whatever. Now let's do the actual computation. So we say delta, our actual delta values, are going to be equal to, we're going to take the LDO times O, right? It's just intro as multiplication. And then we are going to TL.sum both of these, axis equals 1. In my code I'm looking off of off screen, I actually have here and here a .2 TL.float 32 right here, but I don't think it's necessary. I'm pretty sure that's just redundant and from back when I was messing with data types then on a separate topic. So we're going to ignore that. Delta pointer, move this to the correct batch and head. Stride delta H. I should have used a DLDO here, but it doesn't really matter, the equivalent. And then we say TL.store delta pointer plus row offsets. We're going to store that delta value, and mask equals mask. So what we're doing here in this little precomputation kernel is very, very simple, right? We're loading in our outputs and our derivative, and then we are just entry-wise multiplying them and then summing along that head dimension along DH. What size is this then? This because if this is size pre-block size row DH, and then same thing for this, then when we do this, what we effectively have is size pre-block size row, right? So then we're indexing and removing correctly based off batch and heads. And so all we're doing is getting a single value that will just, the delta name is also arbitrary. There's no real like reasoning behind necessarily. I think they used a delta symbol, I believe, in the original paper, if I remember correctly. But effectively, you'll see what this equation is a little bit counterintuitively equivalent to when we go do the actual primary part of the backward pass, right? But we go ahead and store this. This kernel should all be good with all of that. And then let's go back to our backward pass wrapper, where we can define the launch grid for our primary kernel that does most computation as lambda meta triton.cdiv n meta. And again, we are parallelizing across that n dimension as always, block size macro. So new names here. We're going to have a macro and a micro block size. They're going to switch around as to which one is assigned to queries versus the keys, right? So there was, remember the forward pass, we had one, we had our, what's it called? Let me make sure I can see my camera. We had our n by n attention matrix, right? And we had the one axis that was both our queries and our outputs of their n dimension. Then we had the other axis that was both our keys and our values of their n dimension, right? This time, instead of being very clearly like, oh, this hyperparameter, this meta parameter is for queries and this one's for keys, we're actually going to flip back and forth as to which one is which, because sometimes it will be useful to do that switching. We'll see all that stuff later. Don't get too worried about that quite yet. And that's the first most important axis parallelization. And the second one, as always, b times h. Really, whenever you want to support any prior preceding dimensions, this is just what you always do, really. It's just an extra little axis right there, and move yourself to that axis correctly. Then we call the actual kernel attention backward grid, and we say what are our inputs, right? Q, K, and V. It's also going to want our derivatives, dl, do, dl, dq, k, and v. Then we say our log sum x, which again, remember we computed this, we pre-computed this in the forward pass, and we saw a little bit as to the actual log exponential rules that it's going to be useful for. And then we say delta, right? And then we also want our scale and the stride. So q dot stride 0. And we're going to use this for all of our strides, which we can do in this kernel because we made the assertion that all of their strides were equal to each other, right? We already asserted that. Therefore, if it gets to here, we can just use query strides for everything else. And we say h and dh, right? And once we do compute everything, our goal is to actually compute the query key and value gradients. Eventually, we will return those, which will just be return dl dq, dl dk, dl dv, and none. Remember, we need to do it in this order and with the none because PyTorch expects that it receives derivatives for the actual input. So PyTorch will do a little, PyTorch will say q.grad equals dl dq, k.grad equals dl dk, or actually it won't say equals to, it'll say plus equals. It'll add those into it, right? And if it's already, and so that's why we do that, is because PyTorch expects the correct ordering, and that final parameter was our scale, which is just a single float, doesn't need a gradient or anything, right? Now let's build the actual primary kernel of interest today. And this is also going to be a nested series of kernels. I'm going to go ahead and copy and paste the auto tuning because that's pretty boring, right? Same thing as earlier. Here are blocks, whereas in the forward pass we had a block size QO, block size KV to show which one was which, what they were parallelizing across, which dimensions and which tensors. Here we're going to just call them block size macro and micro for now, and you'll see how we actually switch them around weirdly later. And we say at triton.jit def attention backward, right? Q pointer, K pointer, V pointer. Same thing with all of our derivatives. You want to grab their pointers as well as the two extra helper tensors, LSEs from our forward pass, delta we just pre-computed. Then we say the scale. And also, remember, we only input the strides of our queries. We're going to use them for everything since they're contiguous. So boom, that's just stride of the given dimension that it's interested in. And then we can say, we're going to use h, n, dh. Did we ever even use the n and dh or whatever it was on here? I don't even, yeah, we did actually, never mind. Who cares? So dh constant expression, as well as block size macro, and same thing for block size micro, right? And then starting off here, I'm going to do the exact same thing we did in the forward kernel, is we actually going to predefine some floating point values that'll be useful later. First one is just natural log of 2. This was a new one. Nothing too complicated there. The second one is the reciprocal of the natural log of 2, which is the exact same one we had in the forward pass. Nothing too crazy there. We're going to be using these for similar reasons. We used one earlier, is it's more efficient if we can use the exponential of 2. But notice the derivative of e to the x is just e to the x, right? Whereas the derivative of 2 to the x is, I forget, is it like 2 to the x divided by log of 2 or times log of 2? But it's something like that. And so we're going to be using log of 2 and reciprocal log of 2 to account for that, basically, to include that in the actual derivative. All right, first thing, let's move all of our pointers to the correct batch in head. That's just the simple, easy part. IDX BH equals TL dot program ID. Axis is 1, right? IDX B equals IDX BH divided by H. Damn, autocorrect. I don't want to write the word have. Why would I write the word have? IDX H equals IDX BH modulo H, right? And then we say BH jump equals IDX B times stride of B plus IDX H times stride of H, right? And this gives us the actual correct, not only batch, but also head to jump to. And then for everything like Q pointer, we can just plus equal the BH jump, and that gets us to the right place. And we can just do a bunch of paste for these and go through and say this one is K, this one is V, and we've got DLDO, DLDQ, DLDV, and QK. We'll just do K here to keep things in order, right? K and V, and I think that's it, right? And we delete that line. And then same thing for the actual other tensors, the LSE and the delta, right? We have to move them by a different amount because they don't get to need to worry about as much. So we say BH jump, this is a new BH jump, is going to be equal to IDX BH times N, because the actual strides are different here, right? These strides incorporate that head dimension. This one does not. We're going to go ahead and use, it looks like, rather than actually ever inputting the strides of LSE and delta, we know that we defined in our kernel wrapper what LSE and delta were, right? There was never any point where any outside user defined these tensors and did like torch.view on them or anything, right? We know that we define LSE and delta. So if we want to, we don't even have to actually use the official stride if we know what the stride is. And the stride here is going to be equal to n, right? If you were to do what would it be? If this should be like not in the kernel, right? But if you were to in the wrapper do LSE dot stride, what would that be? Because LSE is equal to, or has the shape of batch by number of heads by sequence length. So really the stride would be B, wait a minute, it would be H times N and 1, right? So by using this N right here, we are actually effectively using LSE.stride of what would this be? This would be stride of 1, right? So we can actually know what it would be and just do it manually in our heads because we know for a fact that we've got tensors that are contiguous and that we know what their actual strides are. And then we can go say LSE pointer plus equals BH jump, right? And then delta pointer, same deal, plus equals BH jump, right? You could, if you wanted to, pass in the actual stride here and use that, but I went ahead and just skipped it. It's fewer things to pass in that way. All right, here is a place where we are actually going to use TL.static assert. We're going to say block size macro modulo block size micro equals 0, aka block size macro must be a multiple of block size micro. You're going to see why this has to be the case later, but we are going to write the rest of our kernel under this assumption. Is basically we are going to define these block areas that kind of have sub blocks in them, where like let's say you have a chunk of our n by n sequence length like tensor, right? Like our queries by our keys, the actual big attention matrix. If you have a chunk of it that is like a, it's a block, right? It's like a little sub piece of it. If it is, that chunk is of shape block size macro by block size macro, we're actually going to take a little sub chunk of it that is of shape block size macro by block size micro and like take that and then do a for loop over it, right? What I mean by that, if we can go ahead, like let's say we were looking at this n by n thing we had last time, right? This is the actual tension matrix, and then we had blocks in here, like these blue blocks, for example. Let's say you take one of these blocks that is a sub piece of the actual big tensor, and it is macro, macro by macro. What we're going to be doing later is we're going to be cutting it up into tinier chunks where each of these themselves are of length micro, right? And then we're going to have a for loop iterate through. So this is just, we have a kind of a concept of a macro block and a micro block here, right? Where we're going to be actually loading, effectively our blocks are really the pink ones, we're actually loading at a given time, but we're going to be looking at it in such a way that you can think of it in this way. It'll make more sense later, I think, when we actually start using it with the for loop and everything, and we show you what we're actually blocking apart. So that'll make more sense later, but we assert this right here. And that assertion should both make things more efficient, make sure nothing actually breaks, right? We wouldn't want to have those pink rectangles offset and overlap and get masked out or whatever. Now, we're going to do stage 1. This is DLDK and DLDV. You could actually flip the stages and do DLDQ first, it doesn't really matter, but we're going to do the DLDK and DLDV first. Is we're going to say block size row 1 tilde constant expression. If you know that you're defining this, what's this, block size micro, and this will be block size column 1, block size macro, right? Because the micro macro block size are compile time expressions, and then we can also just say that these are 2. If you tell Triton this is a compile time defined, it will have an easier time making things more efficient under the hood. And then all we're doing here is we're saying, okay, here in stage 1, we're going to use these 2 pieces this way. We're going to see later that the difference with stage 2, we're not actually going to do stage 2 in full right now, but I'm just like give you like some prompting as to the idea. In stage 2, we're doing DLDQ, and we would say block size row 2. So this 1 and 2 just defines our stage number to clarify what part we're in. In stage 2, the rows will use block size macro, and the columns will use block size micro. So we're doing things a little bit reversed, but let's do stage 1 for now. I just want to clarify why we're using these this way and how we're going to use them differently. So keep that in the back of your head for later, and we're instead going to work entirely in stage 1 for now, as we are next going to say, all right, what is our PID? You could call this row as well. PID is TL.program ID 0. This is like just a part of the PID, obviously, because the first part of the PID was up here, and axis is 1. Here, this is our axis is 0 piece. And we're going to say, okay, start column, right? Our start column is equal to our PID times block size column 1. We're going to start here. Shouldn't this be oh, this is gross. This should be a capital L to make it prettier. Ew, lowercase, ew. We're going to start at that column, and then start row just equals start column, right? Kind of weird right here. Basically what it means, remember how we're using a causal mask, right? What we're actually going to do here for a parallelization scheme is we are always starting on the block diagonal, which is what this does. Like if PID is equal to 0, then we end up just on the 0th column in the 0 row. Remember, rows refers to the sequence length of queries and outputs, and columns refers to the sequence length of keys and values in our n by n tensor, right? So we're starting on that actual block diagonal, and then number of steps equals block size column 1 divided by block size row 1, this refers to the pink rectangles I had. We're doing 4 loops over them. Number of steps is the number of pink rectangles inside of a blue square as of earlier, that little earlier display, right? Seeing right here, number of steps is equal to 4 in this case, because there's, I guess, is it 3 steps or 4? Yeah. 4 steps, right? So we actually iterate over. It's just the number of pink rectangles are little sub blocks inside of our actual blue square, our primary block, right? Next thing, we're going to load our keys and values. So we say offsets, call 1. Again, the 1 and the 2 just correspond to our stage, but you can honestly ignore them. Equals start call, because we're never actually going to interact with 1 and 2. We're never actually going to have them interact at all. I want to just define them up front in the beginning of stage 1 and 2 piece, but from then on we'll just use call and row for the remaining variables we define. So we say start call plus tl.arange 0, block size call 1, then offsets dh equals tl.arange 0 dh, and we say kv offsets equals, so kv looks similar here, offsets call 1, make sure that's the correct number of actual tensor dimensions, stride n, plus offsets dh, none, stride dh. And then, so we actually get to load in our keys and our values. First, though, we need a mask, or we'll call it kv mask, equals offsets call 1 less than n, right? Always an issue. You want to make sure that you don't go overboard with our warps, including unnecessary pieces of the sequence. And then we say tl.load k pointer plus kv offsets mask equals kv mask, and other equals 0. We do other equals 0 because we're going to do map moles of these, and whenever you do a map mole, you want your mask pieces to be 0. If that's not clear, as always, just think about it real quick or write it down, right? An entire extra row or column of zeros in the correct place will end up being, once you map mole, like an L shape but reversed of zeros, right? So we say v pointer plus kv offsets, these exact same offsets, mask equals kv mask, other equals 0. And then, so what are the shapes here? Shapes are block size call 1 and dh, right? Then here is the first little bit, right? Is we are going to pre-scale the value of k here, as opposed to doing it in the upcoming for loop, right? Remember we last in the for pass had a for loop that goes throughout, I want to say it moved through rows of the attention matrix, right? Here, we can pre-scale our keys, because if we were to do it when actually iterating in the for loop, we'd have to do an entire floating point op. What's this? K times equals scale times RLN2. We'd have to do this for every single for loop, right? That's a lot of flops in there. Whereas we can do it ahead of time here in K to instant computation. I'll show you that later, I believe. And then we also scale by RLN2, same reason. It's just an actual scalar to multiply by. We can do it here instead of later to save on computation. And again, if you want like perfect derivatives, I recommend reading the actual paper, the Flash Engine 2 paper, for its full derivations of derivatives. Whereas we're focusing here more on the parallelization scheme, right? We're going to set up dldk equals tl dot zeros, block size call 1 dh. We're going to accumulate into these, right? TL dot float 32. Same thing with DL dv. So doing this entry-wise multiplication here just allows us to not have to do it during the actual accumulation, the for loop later, right? So we're going to show you that in a bit. Is DL dk, DL dv equals attention. So this is going to be a subkernel backward kv. We do a subkernel, we're going to call this actually twice. We're going to call it two separate times. And this first call of this subkernel is, let me show the iPad again. It is going to work along the block diagonal, right? So if we have the block diagonal, and then, so this first call of that new kernel is going to do these pieces, right? And this is going to be, each PID handles a different one of these chunks, right? And then each PID in this internal call splits those chunks up into its sub like block size micro size chunks and iterates across them, right? And so it goes dot 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 like with its little arrow, right? And then that is going to be our first call of this inner function. And then the second call of the inner function is going to do all of the actual dense blocks below the diagonal, right? So I'm not gonna, right, just all those throughout there. And it also is going to have the same hidden inner micro block setup, like with cutting across like the pink ones, right? To be honest, I forgot top of my head. It might actually be structured not from left to right with the pink rectangles. It might be structured this way from top to bottom. I forget. I guess we'll see that in a second. But the first call to the kernel is the blue squares. Each PID is a different blue square, and we're going to do that first call. The kernel has a for loop in it. The for loop are the movement from one pink rectangle to the next. And then the second call of this inner kernel is going to do all of the orange squares and all that stuff down below. And it is going to have each PID is, I believe, a different, I want to say row. It could be column, I forget. But let's say for a second it's rows, and it will do not just in the big chunks, but it will also move through these to get all the way to the end, right? And I forget, it might actually be columns. It might be actually moving down this way. We'll see that in a second, but that's the rough scheme. So what are we inputting into this? It's going to be keys and values already loaded, DL, DK, and DL, DV already predefined as zeros, as well as pointers to the pieces that we're going to have to load for each separate iteration of the upcoming for loop. LSE pointer, delta pointer, strides, we're going to need N, NDH, and then the actual block sizes, block size call one, start row, and start column. Remember, these are just how we define that we're on the block diagonal. We defined those earlier, and we have the same starting column and row, which is how we get to just start off on that block diagonal. And then the actual number of steps, aka the number of pink rectangles that we move through, right, along our subblocks. And then we say scale, and then ln2, rln2. I don't think I actually end up using all three of those. I think I just use scale maybe. I forget, honestly. We'll see what we actually use later. And then we say mask equals true because we are on the block diagonal for this call. Then separately, we're going to do a different call to the same subkernel model, right? And this subkernel is going to actually have mask is false, right? As well as we're going to have to redefine start row, start column number of steps in this context, where we get to say start row plus equals block size call one. So our start row changes, but our start column does not change. That's defined by our PID. So actually, yes, totally. We were messing it up earlier. Sorry about that, but we are actually doing this in a flipped method. I wonder if can I do that? Is there a way to, that's not gonna work. So I was wrong earlier. I was misremembering correctly. So basically we're not moving along the rows, we're moving along the columns. So same block diagonal, we still have blocks on the diagonal, right? And then we still have our little pink subrectangles, but they are actually, please forgive me for that mistake, they are actually moving down, right? We are going this way, down them for all of them. And then, so like this is true for all of these. And then that is the first call to our kernel. The second call is still doing all of these big macro blocks down below, right? But this time, again, I was wrong earlier. It is actually splitting or moving down this way, right? And actually that second call to the kernel is going to go all the way down, whereas a given PID is one single column. Each of these red lines is its own PID, right? And it iterates in little blocks of these green tiny sub blocks, right? So forgive me, we were messed up with doing rows earlier. The forward pass does across rows. This stage one of the backward pass it looks like moves across columns or down columns. So we get our new start row, right, which just moves us down by the big size. We could have also just done like, what's this? This is macro, right? Yeah, this is, I think, more clear when we say, because we're moving the row, right? We're macro. Same thing. And then we say n adjust. So we need to now know how many of those tiny blocks need to be done. So we say tl.cdiv n block size call 1 times block size call 1. And this just adjusts our actual sequence length to make sure that it is big enough to such that if we have any little masked out pieces at the end, they still get included in the last actual block. So notice this is a ceiling division, right? So we do ceiling division. This gives us, rather than floor division, one above that, and then return it back to roughly in the same order as n. And so this is always either equal to n or just a little bit above n, like the nearest, the closest multiple of block size call 1 above n, right? Then we say number of steps equals n adjusted minus start row divided by block size row 1, right? And so that block size row 1, aka block size micro, right? As we are saying, okay, we have our new start row that doesn't move down by the entire big block size, and then we get to, from there, see how many actual of those tiny blocks we're going to end up doing. And then that calls that next version of our tensor, after which we end up saving dl and dk and dl dv. But let's go and do our actual inner loop now, which itself will be a separate kernel, just a subkernel to be called. We're going to call it at Triton.jit and def attention backwards. Oh, it gave me the name for me. Nice. And then we say, what are our inputs? I'm writing this one actually above the one we're just writing. I like to write things above what I was just doing a second ago. And we say k, v, dl, d, k, dl, dv, q pointer, dl, do pointer, lse pointer, delta pointer, stride, n, stride, dh, h, n, dh, til.constant expression, block size row, block size column. We're going to remove the underscore 1 from these two because we're actually in it, and there's not going to be any 2's in this kernel. For only this kernel is only going to be called during stage 1. And then we're going to say start row, start column, number of steps, and then scale ln2, rln2, and then mask, right? Which is just a true or false value. And then I'm going to go ahead and we can copy and paste. This is the same as what I just drew here, but it's in my written version of the tutorial. We can go ahead and say, boom, that just shows us we are moving downwards, right? We're moving downwards, but then also clarify. So our first call of this kernel is on the block diagonal, right? Meaning it's actually doing these, right? And then our second call of the kernel is below the block diagonal. Wait, how do I do this? How do I highlight this correctly? Right, meaning it's calling these, right? Whereas that top right upper triangular actually never gets called. So going on to define what's in here, offsets row equals start row plus tl dot a range 0 block size row, and then offsets call equals start call plus tl dot a range 0 block size call. And we could have just piped this in from the outer kernel, but we were going to redefine it here. Probably less efficient doing it that way, but whatever, it's already here. I'm not going to go back and change it now. And then we say, we are actually, this is the derivatives get a little bit annoying in here. I'm not going to go really that in depth on the derivatives themselves and why they equal that. I would hope you can have a handle on calculus for this point, because it is just a series of operations that themselves are relatively simple. It's just once you get them all together, it can kind of be a lot. And then what we're going to do instead is focus on the parallelization strategy is the goal. And so we say we're going to actually load in here as part of a for loop that's upcoming. We're going to do for loop in a bit. As we say Q transposed offsets, right? We're going to transpose Q while we load it in, kind of like how we transpose K during the for pass and we loaded it in. We say offsets DH, so our row is actually the head dimension, our rows times stride DH plus offsets row none times stride N, and then we say DLDO offsets, and this one is not going to be transposed, as we're going to say offsets row stride N plus offsets DH stride DH. And then for our actual for loop, we're going to say for block IDX in range number of steps. That was defined earlier in our drawing earlier. What did we have it as? We had a blue block as having 4 pink blocks in it. In that case, num steps would have been 4, right? Which is a pretty reasonable value, I believe, given, I think in these two we defined there's actually only 2 number of steps in a given single macro block, right? And then we are going to do a bunch of loadings ins of tensors, right? So we're going to make a mask for all of them, mask for most of them, I think. And mask n equals offsets row is less than n. Offsets row is defined what up here, right? And then we say Q transpose block is TL.load Q pointer plus QT offsets mask equals mask n. Make it the correct actual number of axes. Other equals 0. And it's shape DH block size row, right? We're going to do here a bunch of loads all in a row. Next one is going to be LSE, then the LDO, and then delta. We're going to do a bunch of loads here, right? So how do we get my cursor? Equals TL.load pointer plus offsets. We're going to go and edit those specifics later. Mask equals mask n, other equals 0. And for LSE is LSE pointer. So now you may be wondering, like, why are we loading all of these at once, right? So it's kind of odd. In the official Triton tutorials, what they did was a little bit interesting to me, is they actually loaded, I want to say they just loaded these first two, then did some operations here, then loaded DLDO, then did some operations, then loaded delta, then did some final operations, right? But when they loaded QT and LSE together at first, the comments on that say it's more efficient to do a bunch of loads and then a bunch of flops than it is to do load, then flop, then load, then flop, then load, then flop. I'm not sure. So like they said that, and then their behavior said otherwise. They did their own advice, and they did 2 loads and then a bunch of flops, right? But then they did load, then flop, then load, then flop in these portions, right? It's unclear to me if there's like some kind of specific scenario or diminishing returns to which that is actually true, that you should do a bunch of loads, then a bunch of flops, because they only half followed their own advice. But I went and I said, you know what, we're going to follow their advice directly and do a bunch of loads, bunch of loads first, then a bunch of flops, because the Triton tutorials are very, very lazily written, and I have a feeling that they like tried, that they were like about to teach a lesson kind of thing and about to actually follow their own rules, and then just kind of like got too lazy and didn't do it. That's my impression. And this kernel is more efficient than PyTorch's base on FP32 data type. So hopefully I'm correct here, and I think this is correct, is we're going to do a bunch of these loads all at once and then do our flops all in a row next. The reason to be more efficient is apparently in terms of the whole number of stages thing, how you have the pipeline parallelization. Apparently this helps. It's easier for Triton to look at these and see, oh, we can actually do these on like some stage or in parallel or whatever when Triton goes to optimize things at a low level. Hopefully that's the case. I'm not perfectly sure, but that's the advice I'm following, and it seems to be working in terms of like what the actual final benchmark is going to be when we see at the end of the video, right? Next thing, so shape. Let's look at, make sure we understand all of these. For our log sum x, right, our shape is just block size row. It's just a bunch of single values for a given row, right? And then shape of our DLDO is block size row. What's this, DH, right? Yeah, it's DH. And then finally, delta is also shape, block size, row. I did load these in the order that we're going to use them, right? And we're also going to use K and V and DLDK and DLDV since they were passed into this subkernel, right? Now, first thing we're going to do is we actually, remember how we didn't ever save our n by n attention matrices into DRAM and to VRAM? How we instead chose to compute them all fused in the kernel and only ever have tiny chunks of those in SRAM, never saving to DRAM? Well, guess what? Now, because we did that, we kind of have to recompute those matrices, the S and the P matrices, from scratch all over again. You might imagine this being slower, but the slowdown and flops you get having to recompute again in the backward pass is well worth the trade-off of not having to store those ginormous n by n matrices in DRAM, right? So we say S T, we're actually going to create the transpose version of S, right? Equals TL dot K Q T, right? So here, notice in the original attention formula, it's Q by transpose of K. Therefore, when you flip the transposes, then S is transpose, right? So it's coming in reverse order. As well as, remember earlier we already scaled K when we first loaded K in, what was it, in our outer thing? We scaled K earlier. So the actual 1 over square root of head dimension, the tension softmax scaling, is already in here inside the K and accounted for through that method. It's actually associative as to which one you do first, so who really cares? And by doing that pre-computation, by doing this multiplied by scale here, when we first loaded K, as opposed to doing it here, notice how we reuse K, the same K, many times in our for loop we're going to, like at least in this case 2 or 4 times, whatever. By doing it earlier down there, we got to only do that entry-wise multiplication one time, versus here, if we were to do like a time scale right here, that would be doing a time scale for every single iteration in the for loop, right? So because they are mathematically equivalent, we did it earlier, saved ourselves some flops, right? So now our shape is block size column by block size row, reason being that K's shape is block size column by DH and QT's shape is DH by block size row, right? Also notice that we do have, if our sequence length is not a clean multiple of the warp size 32, right? We have been masking as we've been loading in, masking along sequence length, right? And so, for example, here on QT, what is this being? Masking along that second dimension. So QT here, if we are on the final block, the final one of our sequence, then there will be some masked out columns, right? Whereas K, if we're on the final block of our sequence, there'd be some masked out rows, and that would overall lead to a masked out kind of reverse L shape in S transpose, basically. So don't worry about it too much. It only applies to the final block of the whole thing, but it is useful to keep track of what actually happens to all those extra masked out entries at the end, right? Next thing is to get our P matrix, in this case P underscore T, or P transpose, which, remember, this isn't the final probabilities output of the softmax. This is actually kind of a silly name for it. This is the numerator of the softmax equation. It's going to be equal to S transposed minus our log sum x, right? This is why we pre-computed that earlier. Remember, we did the whole thing with our log rules in the previous video. Where was that? Can we find it real quick? Yeah, we found it right here. When we create our log sum x is effectively equal to the maxes of our safe softmax and the actual division by our sums, right? So we actually saved both of those in one. So actually I was wrong a second ago. This P here, where are we? This P actually is the final probabilities, right, tensor, right? But we don't just do that. We also have to keep in mind that log rule, right? So we do TL.exp2, right? And that goes right here. So that is of shape, block size call, and block size row, just like this one was. Also remember that in the outer function of this whole backward pass. Remember, we pre-computed ln2 and rln2, and we didn't just multiply keys by our scale, we also multiplied by our reciprocal log 2. That is actually accounts for, that is the derivative piece of 2 to the x, because e to the x derivative is just e to the x. 2 to the x's derivative is, what is it, 2 divided by log of 2 or something, and that is accounted for when we do this right here. So that same reason as the scale piece, right? We can do it here and do it once, as opposed to doing it inside the for loop of our inner kernel, right? As opposed to doing it in here, doing it many times. So this ends up being that final probabilities function. But we actually do require one more. I think we have to use, for the derivative part, we have to use this, I want to say, right? So we're going to use that a bit later as well to make sure our derivatives all line up. And now next thing is if mask, right? Meaning if we are on the block diagonal, I could have called it the variable diagonal instead. We say mask equals offsets column none less than or equal to offsets row none, right? So this looks like an upper triangular mask. In reality, it's because we transposed, right? In reality, it is effectively a lower triangular mask. So then we say pt equals tl dot where mask pt 0, right? And that gives us our correct mask. This will only trigger if we are on the block diagonal, aka if this mask variable is inputted as true. So for the first run of this subkernel. Moving on, we're going to compute DLDV is just the TL dot dot, aka the map mul of PT, and DLDO. And we're going to tell it to accumulate into DLDV. That way it knows once you have the output of this, like add it directly into here, as opposed to writing it to SRAM and doing a separate addition operation, right? And then what are our sizes or shapes here? Shape is block size column DH. And then we're going to, actually, why does that mean that? Because PT is what shape is PT, block size column, block size row, whereas DLDO is block size row, then DH. So then map mul them together, you get block size call and DH. And then we're going to compute DLDP and DLDS to get DLDK now, right? So DLDP transposed is TL dot V TL dot transpose DLDO. We could have loaded DLDO in as a transpose, but because we use it here as well, there's really no reason. We'd have to do a TL dot trans at some point, and you don't want to load two separate pieces of DLDO in at a time. You'd rather do the flops and not have to take up extra SRAM. So therefore we did it here. We don't need to do an accumulation on this one because DLDPT doesn't exist yet, right? There is no prior existing thing to accumulate into, whereas DLDV already is a bunch of TL.0s up here, right? And what shape is this? Block size column, block size row, and then DLDST is equal to, bit of a weird one, is PT multiplied, entry-wise multiplied by DLDP T minus delta, right? This is where we actually get to use that delta right here. Make sure it is of the correct number of axes and the correct one. And then we also have to multiply by ln2. This ln2 multiply right here, I believe is just for this tilde x2 right here, I think. Is that right? It might actually be for, does delta, no. Yeah, I think that's just for the derivative of this 2 to the power of right here, I believe. And then can I find the piece that tells us what delta is equivalent to? Yeah, so forgive me, this note is in reference to a non-transpose version of DLDS, which we're going to do in the separate piece. But basically, if we were to instead do weighted, let me just put this in the same line so it's clear. If we're instead to do, we'll call it weighted DLDP equals TL.sum DLDP. Let me clarify this. So to be clear, in this subkernel, we're doing things transpose for P and for S, right? Transposed. This note I'm writing right here is, I suppose, in reference to a non-transpose version. Once I write it, I'll see if I can correct it and make it more clear. But TL.sum DLDP times entry-wise multiplied by P, and then axis equals 1, right? So this is row sum. So we're weighting the probabilities by their own derivatives and then summing along them. And then DLDS equals P times DLDP minus weighted DLDP none, right? So these two lines are equivalent to this line in the sense that delta was pre-computed earlier. It's a bit counterintuitive because delta was made out of, what was it made out of? It was made out of DLDO and O, but actually it is equivalent. Delta is equivalent to this right here. Basically, is the principle. And all we would have to do to mess with this, I think, is we have to transpose this, transpose this, transpose this, transpose everything. I guess just transpose everything, and then this should all be the same, right? And I think we could say none, colon. I could be a bit off one of these little transposes in here, but basically this line is equivalent to these two lines, right? As we were just doing that. And as far as why this is the derivative, again, check the paper for a math lesson. This is more parallelization scheme. The reason we do this, the reason we pre-compute delta in a separate kernel, as opposed to doing it in the moment here, right? Is that, remember how I said we have, what was that? Stage 1 and stage 2. Like stage 1 was DLDK and DLDV, and stage 2 is going to be DLDQ. Both of them want to use delta. Both of them do, right? But if we were to actually do things with these two lines of code in here, then we'd effectively be doing duplicate recomputations of delta. And what is not the case is for DLDP and DLDS, we're stuck doing that. But for delta, because this piece right here, this has a very convenient equivalency to whatever we pre-computed earlier, or was a pre-computation one, because it just so happens to be equivalent to DLDO times O, we get to take advantage of that and only do this computation, this pre-processing once, as opposed to doing it in both of our inner function calls, right? For DLDQ and for the current DLDK and DLDV, right? So we computed delta one time in our pre-computation kernel, as opposed to computing it here and in the stage 2, right? So we got to remove that. So we traded those duplicate pre-computations for just being forced to do a read and write to memory in our pre-computation one. But because delta is so small, it's just batch size times head times sequence length. It's a relatively small memory operation, whereas it would be a relatively large flop operation, right? And you think in terms of a big O notation, right? Flop wise, this is n squared because we have our sequence length by sequence length like matrix, whereas read memory writes, it's just linear, it's just on because it's just has a single n to do, right? So that's kind of the reason we go about all that. So we have to now do extra memory accesses, but we get to skip a larger complexity level of flops basically. And then the next thing we do is we use DLDBT and DLDST to make DLDQ, and we plus equal, I think we can actually do the accumulate thing, right? It equals, wait a minute, TL dot dot DLDS TL dot trans KT. So we're getting actually the original K now. Honestly, why did we even bother to, do we have a KT and a K? What is this? This is a QT. We have a K right here. How does this work? Oh, am I looking at the wrong thing now? I'm looking at the wrong thing. Yeah, my bad. Let's get back to where we were. This is wrong. What is this? This is DLDST TL dot trans QT. So back to regular Q, right? Yeah, then this is, what is this? This is K, right? DLDK is TL dot dot DLDST and TL dot trans QT. So back to regular Q. And then we accumulate into DLDK. And the shape of, we should do shape of this one as well, right? Shape, block size call, block size row, whereas this one's shape is block size call DH, And then what we can do next is we can say we're in a for loop, right? We are moving along that smaller, the block size micro dimension. So we're going to iterate and we say offsets row plus equal block size row, aka block size micro. And we're saying q pointer plus equal block size row times stride n, then dldo pointer stride n, then return dldk dldv. Boom, right? And that is how we computed dldk and dldv. The first call to this inner kernel, right, is going to have mask equal to true, so it'll be doing all of the pieces on the actual diagonal. And when it does so, we'll have this be called as true. Whereas for the second call of this inner kernel, we're going to be doing all of the lower below the block diagonal pieces, right? Then we go back to our outer kernel, the big one, right? Attention backward. And we say, okay, we just called both of those in both scenarios. And we say we want to do a final scaling. DLDK times equal scale times RLN2. Again, it's cheaper to do that here. Remember we did it in the original, we scaled K, right? So we have to now unscale it. It was cheaper to do that on the outside in both here than it was in the actual for loop itself. And we say tl.store dldk pointer plus kv offsets tldk. Mask is kv mask, which we defined all that earlier. And then same thing, store dldv pointer plus kv offsets dldv. Right, boom, we have now successfully calculated our actual keys and values. Then we get to move on to stage 2, right? In which case we switch our macro and micros, right? So now macro is rows and micros are columns. So this is why I was confused earlier a little bit, is what we just did with our keys and values derivatives was this. Now we're going to do across rows when computing our queries, basically, right? Because remember, this was K and V, and then this one was Q and O, just like our forward pass. Same thing, right? So when we were computing the derivatives of K and V, we needed to actually stick with a specific chunk of K and V and move along them. Whereas now we're doing derivatives of Q, right? Okay, so what we need now is we are again going to start off on the block diagonal, right? So start row is PID, and this is the same thing, just mirrored, switching our columns and rows basically, right? As we did right here. PID times block size row 2, and start column is going to be the exact same as our start row because we're on the block diagonal. And number of steps is block size row 2, block size column 2. So here column is our little micro step size, right? Whereas rows are our big blocks. And we say offsets row start row plus TL a range 0 block size row 2. QO offsets, right, is offsets row stride n plus offsets DH stride DH, and then mask row equals offsets row less than n. And then we're going to actually load in Q, TL.load Q pointer plus QO offsets. Boom, we've loaded it in Q with the correct mask. And we say Q, just like our keys earlier, we're going to also scale Q, RLN2, both of these. Then we say DLDO. We're going to load that in. Masking out rows the whole while. And then loading in our log sum exp. Notice how earlier, right, for our log sum exp, we loaded it in inside the loop, inside that inner loop piece, right? Where was that? Yeah, we loaded it inside of our loop because we were moving down rows of Q and O and LSE and delta, right? We were having to load in LSE and delta for each different iteration of our for loop. Here, because we're keeping the rows of Q and O constants, we actually get to load in our log sum exp, as well as I believe our delta 2 at some point maybe, or do we not use that? I forget. but at least for now, our log sum x, we get to load that in just once per PID. Sets row, mask equals mask row. No need for an axis expansion there. Other equals 0. And then we're going to go ahead and pre-axis expand this rather than do it later, because we're going to have to be using this multiple times. You don't want to axis expand constantly. You can just do it one time here. Then we say DLDQ is TL dot zeros, block size row 2, DH, dtype equals TL dot float 32. We're going to accumulate all of our results into there. And then DLDQ equals attention backward Q. So this is a new inner kernel to call, right? A different one from last time. DLDQ, Q, DLDO, LSE are our passed in tensors, and then our passed in pointers, aka the tensors that are going to be different per iteration in the actual loop. Delta pointer, odd that delta's in there, honestly. Well, maybe we'll see why later. I forget why. Stride N, stride DH. Then we say H, N, DH. I don't even know if we use those. Do we use? Probably use those. And then block size row 2, block size call 2. And we say start row, start call, number of steps. We computed all those above here, right? Yeah, we did. We got new values for all those, for all on the block diagonal. Scale, ln2, rln2. I don't think we use all or even most of those. And then we say mask equals true. There's definitely some unnecessarily passed in items in here, but whatever. Mask true as in we are doing block diagonal first. So our first iteration is block diagonal. And then our second call, DLDQ, just go ahead and copy all of this, really. Our second call of this inner kernel will be working instead on the off diagonal pieces, the dense parts below the block diagonal, right? And to make sure that it has the correctly changed start row, column, and number of steps, we say end call equals start call, right? Reason being, right? So if we are starting, for example, our second PID, right, is starting start row, end row, then we say, all right, our start call anyways, our starting call, ending call. We say, all right, that's for the first call of the this new inner kernel. The second call, the new inner kernel, this will be our new end column, and then this will be our new start column, right? Then start call equals 0. Then we say number of steps equals end call divided by block size call 2, right? Because our block size column in this case is our actual micro size, our for loop iteration size. And then we've got both these loops to call. Let's go ahead and make the actual inner kernel. And what do we do for it is we say we're going to make it below the K and V kernel. We say Triton.jit attention backward Q. And I'm going to go ahead. This is the same input arguments as the previous, or not as the previous, but as the prior inputs. I want to just speed things up a little bit. And we say, let's go ahead and copy our notes just so that you can pause and see them if you want. These are also in the written version of the document that has hella notes in it. And boom, we see we're going across that way. But of course, this first loop is going to be all the pieces along the diagonal. That might be a little bit off the diagonal, but whatever. And then the second call of this kernel is going to be all the pieces below the block diagonal, right? First up, a bunch of offsets. Start row plus TL.A range 0 block size row. These will stay the same the entire time, whereas offsets column will actually change over the course of the for loop, so they're getting iterated along. So start call plus TL.A range 0 block size call, and then offsets DH equals TL.A range 0 DH. And then we are again going to transpose both K and V while loading it, right? K, it's kind of a weird name, and V transposed offsets. Oh, are we just actually transposing V while loading it? Maybe just V. No, this should be both, I think. Offsets DH none times stride DH plus offsets column none times stride N, right? And then we also load in our delta. This is kind of silly. We totally could have loaded delta in the outer, like outside of this inner function, back when we loaded LSE as well, but we didn't for, I think that's just about no reason. Yeah, we totally could have loaded delta back when we loaded LSE, it looks like. Sorry about that, but it doesn't even matter, honestly. Delta pointer plus offsets row, mask equals offsets row less than n. We can just do the mask inside there, other equals 0. Then our actual for loop block idx in range number of steps, and we can say, yeah, we're doing both kt and vt. So kt is tl.load k pointer plus k, and vt offsets mask equals, and we're going to also do an inline mask here because I'm being lazy, offsets call less than n, make it the correct dimension. We should probably actually make this a separate mask, honestly. kv mask equals offsets column less than n, and then expand out its axes, and then we say mask equals kv math. It's a little bit faster than doing it actually inside and separately, so other equals 0, and then we say vt is tl.load, same thing effectively, pointer plus k, and what, mask equals kv mask, other equals 0, right? And these are both of shape, what is this? DH, and offsets call. That is block size call, which I believe is the micro block in this case. And then we say, all right, let's go ahead. And this is the stage where we say, like, oh, we never actually stored our n by n matrices S and P in DRAM, so we now have to actually pre-compute them from scratch rather than just loading them in. And we say S equals TL QKT. And this pretty simple shape is like a forward pass, just the same forward pass as we say block size row, block size column. There should be a comma. And then we say P equals TL.exp2. We've already gone over how the LSE trick works, but this shape, exact same shape, right? And then we say, and then this, thanks to the log sum exp rule, this should actually be the full probabilities, not just the numerator. This is the full thing, the full shebang. And we say if mask, okay, if we're on the block diagonal, we say, how much should we do inline, honestly? P equals TL dot where, offsets row, none greater than equal to, offsets call, none. That's our mask. And then if our mask is true, get the value of P in there. And if it's false, put a 0 instead. And then we use zeros because it's already probabilities, right? And then the mask should, yeah, that looks good. And then rows greater than columns, meaning this is a lower triangular mask after all, because there's no transposing happening. And then we say DLDP. We're going to calculate DLDP and DLDS in order to get DLDQ. So TL dot DLDO VT. What's the shape of this? Block size row, block size column. Is that right? Yeah, I guess so, because DLDO is block size row by DH, and VT is DH by block size column, therefore that's the combined shape. Let me say DLDS is P times DLDP minus delta none times ln2. Again, ln2 here is for the derivative of the actual p, I believe, because whereas e to the x, the derivative is e to the x, for 2 to the x, it's something like reciprocal to 2 to the x or ln2 or something as well. You have to chain roll that out. And then we say, this is that same line where we use delta, right? That has an equivalent line you could have instead, which would have been weighted DLDP is TL.sum DLDP times P axis equals 1, and DLDS is P times DLDP minus weighted DLDP times ln2. So this would have been equivalent. These two lines would have been equivalent to this one line, but we pre-computed delta, and it's just lucky that we can actually, because delta was made with DLDO and O, it's lucky that that is mathematically true, that it's equivalent to this piece right here, right? Yeah, bet. And then effectively we say DLDQ. This should be an accumulation thing, right? Because DLDQ is already a thing. Yeah. So it equals TL dot dot LDS TL dot transpose KT. Did we ever use KT? Yeah, we did. So it's okay to transpose that here. And then we say accumulates equals DLDQ. Boom. Shape, block size, row, DH. And then up here as well, which we list that out, is the shape of this one is block size row, block size column. Easy enough. And boom, we can increment our pointers, offsets, column plus equals block size column, and then K pointer plus equal block size column times stride N. And then that should be the same for V, just moving along K and V, aka moving along the row through columns, and we say return DLDQ. Boom. That is our actual inner loop that computes the derivative of the queries, and then we can go back to our primary kernel, and it calls that first on the block diagonal, then it adjusts it to not be block diagonal, to actually be the dense lower part, and then it calls the actual dense parts below the block diagonal, right? And finally, DLDQ, we can scale that. This is the end of our outer kernel, right, for a backward pass. Scale that by the actual scale, and RLN2. That helped us avoid having to do this inside the for loop. And then TL.store, DLDQ, pointer, plus QO offsets, DLDQ, mask equals mask, row, right? And then I believe if we're very, very lucky, that should totally run first time, no issues. What are the odds? Who wants to bet right now? Place your bets in the comments. Pause this, place your bets in the comments. What do we get when we run? Let's make sure we saved it actually. Save. What are the odds? Nope. I had a lowercase n somewhere. Yep, this is just a lowercase n. Offset call 1 is not defined, I believe. Offset call 1, I believe it should be offsets plural, right? Yeah, plural. Always the typos. Can't we just get an LLM starting to fix typos? I would love an automatically fixed typos model. Attention backward KV, missing 3 required position arguments, scale ln2 and rln2. What does it think it's getting, right? So we have all of that. It thinks it's missing all 3 of these. Shouldn't this one also be required? What's happening here? Did we have a whole row of things forgotten or something? Oh, start row, start column, steps, scale, ln2, rln2, right? We probably forgot our start row, whatever it is. Nope. Block size, stride, pointers, tensors. We forgot these, hn and dh. I don't even know if we use them, but let's go ahead and throw them in there. I want to say those were right here, right? Below the strides. Were they below the strides? Yeah, that should be good now. We forgot to fill these pieces in right here is DLDO and delta. Where is this? What are we in right now? We are in attention backward KV. This is DLDO offsets, and then this one is offsets row. The masks look okay. Hopefully that's all good. Oop, I did unnecessary. Sorry, we're just fixing typos right now. Maybe fast forward a minute, I guess. Like, you have a lowercase l right here that was messed up. Crazy amount of typos today. Stride n. Yeah, sorry for having to deal with my typos. I'm sure you all saw them as I was typing. So I'm gonna plus sign right here. Another stide. Here we go. Beautiful. Passed all the same tests we ran from last time. As a reminder, what were those tests again? We just did a very simple test of each head dimension and then one that actually had a bunch of batches and heads and a masked out sequence length, right? So we do the exact same thing now with the benchmark. This actually I shouldn't have hit that. This is going to run the forward benchmark first and the backward benchmark second. And we didn't actually edit the forward one at all, so that's going to be annoying. But I guess the video will cut to when the backward pass is finished. There we go. I think we should be about done then. What does this results graph look like? Tension performance backward. How do I see this better? Boom. Blue is us. Red is PyTorch. Again, this tutorial isn't like amazing in the sense that this is an entirely FP32 implementation, which is not what you would actually want to do training a model because FP32 is very, very slow, obviously. But we have at least gotten faster than PyTorches. And that was with the fact that we actually set up our auto tuning. We didn't actually use it, right? It was just the one smallest value for everything. So you could get more speed by just enabling auto tuning. But in implementation, we already saw in the MATMO lesson how you do mixed precision. In that case, I think we used FP16 and we accumulated an FP32. You'd want to do something similar here, actually, if you were to build an attention kernel for an actual full training pipeline. I think DeepSeek now trains in FP8s, something like that. I don't know if they're actually accumulating in higher precision. I would assume they are, but that kind of thing. But for the most part, this works pretty well. Other minor things, like for example, we asserted that head dimensions should only be 32, 16, and 128. You will find that 256, 512 are also common for very big models, as well as the fact that we asserted those is kind of arbitrary. Our kernel only supports head dimensions that are a multiple of 32 on AMD processors because that is the warp size, and we didn't bother to do any masking along head dimension. If you wanted to support non-multiples of 32, you would have to add in masking along the head dimension, but like small stuff like that, not a huge thing. Overall, this is it. Also, we don't have dropout, right? We saw in a previous lesson, there was a dropout lesson. I want to say it was lesson number 7, maybe, that we saw how to do random dropouts while only storing the seed in memory and not having to store the actual mask tensor for the actual mask values of what gets dropped out, what gets doesn't. And so you would want to, in training especially, for a training kernel, you'd want to implement that into here for your actual tension matrix to make sure that you're not overfitting or anything. But those are good homework assignments actually. If you want to go make sure you've actually learned this stuff, go do those as homework. I highly recommend. Just watching these videos is not enough. You have to actually build something to actually understand it. And before we finish off, I am tempted right now to do an example of building something. Is I'm tempted to try and sit down and in one sitting finish from scratch, never having done it before. Apple's cut cross entropy loss. I think that'd be interesting. I read the paper months ago, back before I knew how to code a GPU kernel, and I think it'd be interesting to see how feasible that is and how much we can get done, or if it's like a planning stage, like what it would be like, and treat it kind of almost like an interview setup of like an interview says, "Hey Evan, code up a Apple's cut CE loss, and see how far we can get," kind of thing. In the ideal world where we had like a 9 hour long video, we might also do a fused forward and backward, meaning that the single kernel and function wrapper, whatever, don't just do a forward pass, but they actually do a combined forward backward pass that gives the output loss to measure, as well as just jump straight to giving you the actual derivatives. Would be interesting. I'm considering doing that right now. It'd be a fun little practice thing to do. But right now, these videos are getting so few views. I'm kind of like, I don't know. But that would be a good example of a project. Is go read Apple's cut cross entropy loss paper and go implement that. That would be a great one to do now that you've learned all this stuff. But anyways, that's about it. Hope y'all enjoyed. End of video.